We go to the last presentation of today, Miss Lotito from Italy. She's a PhD at the Polytechnical School of Bari.
So this work presents the results of an experimental study aimed at verifying the suitability of an aerobic granular sludge reactor for textile wastewater treatment. The problem with the textile industry is that it's one of the most environmental unfriendly industrial processes, as it consumes really high amounts of high quality water, about 150 liters per kilo of textile product, as water is used in many of its processes, from bleaching to dyeing, printing and washing. Moreover, numerous different chemicals are used in each of these steps, and therefore this water is then released as an highly polluted wastewater. Another problem with the textile wastewater is that its characteristics are really variable from one factory to the other one, but also within the same factory from day to day, due to the fact that most of the processes are of batch nature, and therefore the chemicals used change from day to day. Nevertheless, it's possible to observe some common features, like the presence of recalcitrant pollutants, such as surfactants, heavy metals, detergent solvents, which results in a wastewater with high solids content and high COD, very low biodegradability, with the BOD being even less than 10% of COD, and high color. Currently, textile wastewater are treated with a combination of numerous different steps that range from biological treatment, usually based on activated sludge treatment, and physicochemical methods, so different combinations can be adopted. For this reason, textile effluents are usually treated in centralized treatment plant, as both the cost of the treatment and the space requirement are high. However, the optimal solution would be the on-site treatment at each factory, because this solution would reduce treatment costs and promote water recycle if possible. Biological treatment are to be preferred to physical or chemical ones, because they present lower costs and lower sludge production. However, as textile wastewater are characterized by the presence of high quantities of toxic compounds, this can reduce the treatment efficiency and stability of biological treatment, and there's a high risk of bulking or inhibition of nitrification. These problems can be solved using sequencing batch reactors, because they operate in cycle, and therefore the stress that is imposed to biomass during the filling phase is able to select specific population that can successfully degrade xenobiotic compounds and resist and persist in diverse and adverse conditions. It is even possible to improve the performance of a normal SBR, changing its operation or its design in order, for example, to achieve sludge granulation, like in a sequencing batch biofilter granular reactor. And in this way, it is possible to achieve successful degradation of toxic pollutants and simultaneous carbon oxidation, nitrification, denitrification, and removal of solids just in one reactor. In our study, we have used two lab-scale SBBGR, and as you can see here in the sketch, we can distinguish two parts in the reactor. One is the microbial bed, which develops on a plastic support material that is kept between two seals, and the other one is the liquid phase, where the aerators are located in order to give air to wastewater. During the filling phase, a fixed volume of influent is loaded from the bottom and distributed through a diffuser. Then we have the main part of the cycle, that is the biological degradation phase, during which the aerators are turned on, and an internal recycle assures the distribution of both oxygen substrate to biomass. At the end, the treated effluent is discharged. We have also run combined and integrated treatment with ozonation, because textile effluents contain this recalcitrant fraction, and so in this case the ozone phase is inserted just at the end of the cycle, when all the fraction that can be biological degraded is removed, and there's another recycle in the ozonation column where ozone is dosed, and then the treated effluent is pulled back in the biological reactor to continue the biological degradation. We have treated 4 different types of wastewater. One is the mixed municipal textile wastewater, as this is a commonly applied solution for industrial textile wastewater treatment. And then we have considered 3 specific textile effluents from dyeing and printing factories, as they are the most polluted streams in textile processes. And as you can see, the characteristics of the wastewater were different from one to the other, but also within the same one. So the standard deviation values are quite high. And you can observe the very low biodegradability, especially of the printing and of the fabric dyeing wastewater, with the BOD being less than 10% of COD. It's just a little bit higher for the mixed and for the yarn dye wastewater. And also the ratio between nitrogen and COD is unbalanced, except for the mixed wastewater. For example, in the case of the printing wastewater, we have a quite high nitrogen content due to the use of urea in the process, while in this case we have low nitrogen content. And also the concentration of surfactants is quite high. We have run quite long experimental campaign with different hydraulic retention times and organic loading rates. In particular, we have progressively reduced the hydraulic retention time and increased the organic loading rate by increasing the volume of influent added per treatment cycle, or the number of treatment cycles per day. And we have also tested different ozone doses during the ozonation phase in order to reach the treatment goal. With the biological treatment, we were able to achieve stable performances despite the variability in composition and progressive reduction in the hydraulic retention time, with the good removal of solids thanks to the filtering capacity of the biofilter, with the concentration lower than 10 milligrams per liter for the mix and the printing wastewater. Color removal was quite sparse, changed from stock to stock, with an average around 20–30%. And nitrogen removal was good, even if a slight reduction in nitrification performance was observed whenever a change in the operational condition was applied, but the system was able to reach again stable results after just a few days. And we obtained complete ammonia depletion and a progressive reduction of oxidized nitrogen content, demonstrating the presence of a simultaneous nitrification-denitrification process with total nitrogen removal up to 80–90%. Concerning the removal of COD surfactants, we have achieved different results with the different wastewater treated. In particular, mixed wastewater was successfully treated with effluent COD concentration constantly below 70 milligrams per liter, and surfactants below 2 milligrams per liter. While for the fabric dye wastewater, we achieved constant performances with COD around 200–240 milligrams per liter, and the surfactants always below 4 milligrams per liter, independently of the operational conditions applied. While for the printing and yarn dye wastewater, even if high surfactant removal was achieved, the effluent concentration were still quite high. It can be concluded that depending on the wastewater, it is possible to adopt different operational conditions, and in particular for the mixed wastewater, it is possible to achieve an effluent for direct discharge with the organic loading rates up to 2 kilograms of CO2 per cubic meter per day, and hydraulic detention time even around 10 hours, while the same wastewater is treated in the full centralized treatment plant with numerous treatment steps. This real wastewater, with the biological treatment followed by coagulation, flocculation, and then ozonation with a total hydraulic retention time up to 30 hours. The fabric wastewater can be treated for discharge into municipal sewer system with organic loading rates around 2.6 kilograms of CO2 per cubic meter per day and hydraulic retention time around 20 hours. While for the yard dyeing and the printing wastewater, the surfactants effluent concentration poses some limits, and therefore, when studying the treatment technology for textile wastewaters, is really necessary to study also surfactant effluent concentrations, because they pose higher problems with respect to CO2. For example, with the yard dyeing wastewater, we were able to achieve CO2 effluent concentration even below the limit for direct discharge, while surfactant concentration was higher than the limit for sewer discharge. If we compare the results obtained with SBR technology in the treatment of textile wastewater, we can affirm that SBBGR is more effective, as higher organic loading rates and lower hydraulic retention time can be used. And it's also worth to consider that most of these previous studies were conducted on synthetic wastewater, so made up of glucose or acetate as carbon source and just a single distuff, while real wastewater are much more complex. And in one of the studies, they compared the results with a real wastewater and a synthetic wastewater with the same composition in terms of global parameter, but completely different results were achieved with just only 10% of CO2 removal with the real wastewater. Of course, with the integrated treatment, we were able to significantly enhance the efficiency with quite complete decolorization and surfactant removal, and of course an increase also in CO2 removal. And the best results were achieved with the fabric wastewater, for which it was possible to obtain an effluent for direct discharge with very low ozone doses, around 20-50 milligrams per liter. And what is important is that the ratio between the ozone dose and the enhancement in CO2 removal is around 0.3, so much lower than 1, which means that there's a strong synergetic activity between biomass and ozone in the degradation of CO2. And with the printing wastewater, we needed to increase the ozone dose up to 135 milligrams per liter in order to reduce surfactants to 1 milligram per liter. Even in this case, the synergetic activity can be observed in the ratio lower than 1 between the ozone dose and the enhancement of CO2 removal. At the end of every stage of treatment, we have measured the biomass concentration in the reactor, and you can observe that very high values were achieved with increased concentration from one step to the other, so from biological, for example, to the ozonated treatment. And the specific sludge production was very low, from 0.05% kilograms of solids per kilo CO2 removed to 0.17, which is much lower than the values normally achieved in conventional activities like plant, around 0.4, 0.6 kilograms of solids per kilogram of CO2 removed, and much lower than the ones in physical or chemical processes. And so, concluding, we can affirm that textile wastewater characteristics greatly affect the removal efficiency of a treatment technology due to their complexity. Nevertheless, SBBGR is a valuable biological treatment because it allows to reduce the pollutant load with stable performances, Nevertheless, it is not possible to define standard operational conditions that can be applied for every textile wastewater type, because both operational conditions and maximum treated capability are wastewater specific, and it's necessary to integrate the treatment with ozone to remove the eye surfactant content and color. The correct ozone dose depends on the type of wastewater and on the specific stock under analysis, but in any case the needed dose is lower than the one reported in the previous study. And when scaling up of the technology has to be done, it's advisable to conduct a pre-study in order to define the operational conditions and the maximum treated capability for the specific wastewater under analysis in order to correctly design the reactor. It is also possible to optimize the process and then reduce treatment costs if a dynamic ozone dosage is used, because of course as the dose of ozone is dependent on the specific stock, it is possible to save ozone, just changing it depending on the influent composition. Thank you for your attention.
Any clarification questions? Then